summation of the m dots in equals summation of the m dots coming out. No storage, steady state. We end up with partial u with respect to x equal partial v with respect to y. And that's the differential continuity equation. Equals 0, plus equals 0. Okay, first equation. Second equation, momentum. X momentum equation. Summation of all the forces in the x direction equal the change in x momentum. The forces there are going to be the shear stress forces. So there's a force here and a force here, and this is shear stress. What's momentum? M dot times u, mass flow rate times the velocity. Again, this was done probably in ME 312. If you put that in, what forces are there? The shear stress forces. And the shear stress forces, tau equal mu du dy. So you put that guy in there in the x direction. And on the top, in the x direction, different sign. Put it in there. You end up with this equation. So this is x momentum, assuming p equal constant. In other words, p is not a function of x. Now, of course, you don't normally visually see the edge of the boundary layer here. It's a mathematical definition, 99% of u infinity. Normally, you don't see that. But on my sketch, of course, you do. Normally, it's very, very, very thin. But I can't do it too thin on the board. You wouldn't see anything, so I made it look bigger. But normally, it's a very thin layer of fluid attached to the surface. That's the boundary layer. It's where all the action occurs. That's where the shear stress is. That's what causes the drag. That very thin layer of fluid. The governing partial differential equations. Is P constant? Yeah, P is constant. Assume this is a flat plate here. This is X that way. This is Y that way. This is X0. I put a floor fan here. I blow the air over that table. A boundary layer builds up from the leading edge, and it gets bigger and bigger and bigger as X increases. Okay. Is the pressure constant? The pressure at my fingertip, 14.7 psia. In the middle of the plate, pressure, 14.7 psia. And the plate, 14.7 psia. Yes, the pressure is constant. Okay. If it's not constant, there's going to be a pressure force in the x direction. No, it's constant. It disappears. It's gone. Okay, so that's it. These two equations. The unknowns, well, look at them, V and U. We want to solve for U as a function of X and Y. Where is it in the picture? Right here, right here. Put any point you want in the boundary layer. That big, fat, black dot. Tell me the velocity there. Okay, that's what the solution gives you. I give you an x and a y, and hopefully you tell me what little u is. Now, to do that is not simple. And in ME 312, normally you don't go through all the gory details. But anyway, the results are in Table 7.1 in our book. Table 7.1 looks like this. The first column is this. The second column is little u over u infinity. There's u, there's x, there's y. So what we do now is we say, okay, I want to find out what delta is as a function of x in that picture. So let's solve this for delta. Now where's delta? Delta is where u over u infinity is 0.99. So go to the table, 0.99, this is what you would do. And then over here you'd find a value of 5. So what we have here then, at u over u infinity, 0.99, then this column, and what is y? Y at that 0.99, y is delta. Delta square root u infinity over nu x equal 5. Solve that guy for delta. So delta is equal to 5 over the square root u infinity nu x, which turns out to be 5x over the square root of the Reynolds number. So here's the equation right here. All right, at x equals 0, delta equals 0. As x gets bigger, delta gets bigger. How? As a square root of x. Here. Bends over like this. Square root of x, like this. It's not linear. It bends over as a square root function. Okay, so that's how we find, quote, the edge of the boundary layer. Now, in ME 312, we're interested in finding shear stress and drag, so shear stress tau equal mu du dy. And we're going to do that at the surface, tau at y equals 0, evaluate du dy at y equals 0. There's another column in here which gives you, if you work it out, it'll give you like du dy. Okay. If you go in there and do that, you end up with this. And let's see here. Yep. Mathematically, that's how you get the shear stress at the surface of the plate. There it is. We engineers use this equation. This equation says the shear stress at the wall is a constant, that's the constant, times rho u infinity squared over 2, kinetic energy. A constant times the approaching kinetic energy. That constant is c sub fx. The F stands for friction. The x stands for location. The c stands for coefficient. All right? So that is titled the friction coefficient. So CFX is titled the local. Really is called the skin friction coefficient. The real way you get the shear stress is here. This is the equation we engineers invented. Is that something that came from the basic principles of the governing partial differential equations? My gosh, no. It's the Darcy-Weisbach equation. Who invented it? Here we are. We engineers, we invented it. Why did we invent it? Because it's simple. There is something called a friction factor that takes into account all the messy stuff. And when you want to find the head loss due to friction, that's what you use. Here, we invent this because it's very simple. Very simple. A constant, similar to that. Look at the v squared over 2g. Look at the v squared over 2g. It's the same thing almost, except that's the constant now. What's that guy called? The local skin friction coefficient. So we take these two equations, we equate them. See that one? See the 2 right there? See the 3, 3, 2? There it is, 6, 6, 4. Okay. And so this is how in ME312 we found the skin friction on the surface over there. If you want to integrate that then, multiply it by an area, you're going to get the drag force on the plate. Okay, ME312, one more time. Okay, so that's where we kind of ended up to start off with fluid mechanics. Now we have to shift gears. We're no longer looking at the velocity boundary layer. This is heat transfer, ME415. We're interested in temperature. So now we change things. This becomes the approaching free stream temperature. T infinity, the free stream temperature. Okay. Here is what happens. I'm going to, just for the sake of argument, I'm going to say Ts is greater than T infinity. The plate's hot, the fluid's cold. The plate temperature never changes with X. It's a constant, Ts. T infinity is outside, far away from the plate. The temperature changes from the surface temperature of the plate to the free stream in the y direction. Okay, so let's plot how that might look at any x. At any x, surface is hot. Okay, so this arrow represents the surface temperature, Ts. The free stream is colder. All right, we'll represent that as T infinity. Now you connect them, not linearly, of course, like this. And this is the temperature in the thermal boundary layer. T is the temperature in the thermal boundary layer. This line now represents the edge of the thermal, we'll make it temperature. Either call it a thermal or temperature boundary layer. We'll call it temperature boundary layer. So now, the boundary layer thickness is still defined by 99%, okay? But now we call it delta T. The T stands for temperature. So delta T is the temperature boundary layer thickness now. If So I'll just show you the other picture. If we have the opposite case occurring in the plate, where in this case T infinity is hot and the plate is cooler, then here's how it looks. Here's the plate surface temperature. TS stands for surface temperature. Here's T infinity. This might be in a gas turbine engine, hot gases, cool surface. Comes down here, goes down like that. There's the temperature in the boundary layer, T. They both are analyzed the same way. You do it by dimensionless temperature differences. But the equations are the same no matter which case you've got. So you can look at either case and then the other case is identical in the equations you're going to get. Okay, so now that's our picture. We still have U and V, of course. We still have our approaching stream. We still have continuity. That's not going to change. We still have X momentum. That's not going to change. But now we've got something different. You know what it is. It's energy. Okay. So energy balance on differential element. We take out, yeah, go ahead.
That's still going to be U equals U, the 0.99?
Yeah, it's going to be a temperature difference. Okay, T minus TS divided by T infinity minus TS is 0.99. Okay, so it's a temperature difference, 0.99. This point here is where the temperature, 0.99 of this total difference. If this difference is 100 degrees, you're within 1 degree right there. We'll take out our small differential element, dx dy. Go over here, dx dy. See, we do it the same for all three things. For conservation of mass, for momentum, for energy, the way we start to derive the governing partial differential equation is to look at a small differential element and look at whatever you're interested in crossing here. The mass coming in, the mass going out, the change in momentum, the forces on the differential element. Over here, energy coming in and going out. All right, let's take conduction here. Conduction out. Why is there conduction? Well, look at the picture. Does the temperature vary in the y direction? Yeah, it does. It varies in the y direction. If it does, then there's going to be some conduction. Okay, so our conduction minus K, do it on a heat flux basis, minus K partial T with respect to y. Then we'll have conduction out, which is this plus the partial with respect to y, minus K dt dy times delta times dy. We're not going to worry about conduction in the x direction because the temperatures are not a strong function of x as they are compared to y. But we do have some energy being brought in by incoming fluid in our little differential control volume. That energy is m dot C sub p t, ME301. M dot is rho AV. Velocity is u. The area is the vertical dy times 1 and then you have energy going out. In the y direction, same thing, in and out. Energy in, and energy taken out as a function of the mass flow rate. Well, you put all those terms in the energy balance, and we won't go through all the gory details. Our textbook does a good job of that. And this gives this as your final result. And in that, there's also sometimes, there can be energy generated by viscous effects, heating. Space shuttle comes in from outer space and previously, or any kind of manned spacecraft, and you got this, you see this glowing light. Yeah, there's a lot of heat being generated at the nose area of that particular vessel. But that's high-speed flow. We're not going to worry about high-speed flow here. This is not Mach number 5, okay? This is fairly low-speed flow, so we're not going to worry about viscous dissipation. That term disappeared. It's a mu term, has mu in it, okay? Okay, what's the object now again? The object is to solve for temperature in the boundary layer as a function of x and y. Where are these three equations valid? In the boundary layer, either velocity or temperature. So if I put a big fat black dot in there and I say, okay, I want you to tell me the temperature in the boundary layer where x equal 5 centimeters, y equal a half a centimeter. You could do it then. How? Solve this guy. But to solve this guy, what do you need? I need to know u and v as a function of x and y. Okay, there they are, at least u. And how'd you get that? I solve momentum and continuity. So I take that's why the prereqs are on ME 415 of fluid mechanics, because you take the results of fluid mechanics from this and you put that up here from the temperature boundary layer, and now you solve for t as a function of x and y. Look how similar those equations are. U du dx, u dt dx, v du dy, v dt dy. A constant times d squared u dy squared. A constant times dt squared dy squared. Wow. They almost look like you could solve one and get the answer for the other one because they're so similar. This is thermal diffusivity. This is wrong. This is kinematic viscosity. Okay? Yeah. Which means, there must be something important about that alpha and that nu. There must be something important about that connects those two. One solution might be connected to the other solution because the only difference, they both have a u times this and a v times that, and this is an alpha and that's a nu. Yeah, that's right. We'll find out later on there is a strong connection between them. Yeah. Okay, back to here. How do we find those temperatures? Well, not as neat and clean as we did for the velocity. They're given in figure 7.4b. 7.4b. It's a graph. It's a graph, okay. Okay, so now we have the solution for that. Part of heat transfer, there's two main parts. Part of it is to predict the temperatures in some particular situation like this. We had it in conduction. Tell me the temperature halfway through a plate of thickness 5 centimeters and so on and so forth. Find the temperatures somewhere. Number 2, which is very important, find the heat transfer. That's why the course is titled Heat Transfer. Find the heat transfer. Okay, how do we find the heat transfer here? Well, all right, here's one way to do it. Q x double prime equal hx times T surface minus T infinity. T surface is constant. T infinity is constant. H is a convection coefficient. Chapter 1. Chapter 1. Newton's law of cooling. Try and solve for hx there. Okay, hx is equal to qx double prime ts minus T infinity. Is that hx? No, because I don't know qx double prime. No, it's not. It's true. It's the truth. But it won't help me find hx. What does hx mean, by the way? It means the h value at a particular x location. It's called the local convection coefficient. The word local means as a function of x. Local convection coefficient. Well, look at the picture. Let's see now. How does the heat get out of that plate? The plate's hot. The fluid is colder. It leaves the plate right here where y equals 0. And here comes the catcher now. You tell me the velocity of the fluid at the plate surface, and I'll give you the answer. It's 0, the no-slip condition. The no-slip condition, ME311. That means the fluid is not flowing at y equals 0. What does that mean? Oh, here it comes. Conduction. Conduction occurs where the velocity of the fluid is 0. So the heat leaves the plate by conduction at y equals 0 and is carried away by convection to the fluid at T infinity. Here it is being carried away, the fluid to T infinity. But it leaves by conduction. And Qx double prime equal minus K dt dy. Where? At y equals 0. So now what I do is I go to my graph, figure 7.4b, and get this R numerically. Get that, and if I get that slope at y equals 0, I get minus 0.332 thermal conductivity. From evaluating dt dy at y equals 0, which comes from the solution of the governing energy equation, partial differential equation. I now equate those two. Well, I put this guy here into here. I put that qx into there. And when I do that, I get this for my hx. That equation. There it is. So you want to find hx at any x location, there's the equation you use. I'm going to plot it right here. Put x equals 0, approaching 0. As x approaches 0, hx approaches infinity. Okay, very big. As x gets larger, h gets smaller. There's how it varies. look at Newton's law of cooling. Somebody asks you, where is the heat transfer the greatest in flow over that flat plate? Well, don't forget, Ts minus T infinity is a constant. Q is the greatest where H is the greatest. So the answer is the most heat transfer on a per square meter basis occurs at the leading edge of the plate, right there. That's where the biggest heat transfer occurs. As you go further down the plate, as X increases, the heat transfer goes down, gets smaller and smaller and smaller. Some people say it's due to the thickness of the boundary layer getting bigger. It's an insulating effect. So here's the boundary layer. The thickness here is 0. It gets bigger and bigger and bigger. The thicker the boundary layer gets, by that they mean the y dimension, delta, the thicker it gets, the less heat is being transferred from the plate. Okay. All right, so that gives us H. Next, we bring in a new dimensionless variable called the Nusselt number. Dimensionless is defined as H x multiplied by x over k. And if you put that H sub x from here down into here, you end up with this equation. So this is the dimensionless form of the convection equation. 3 dimensionless parameters: Reynolds number, Prandtl number, Nusselt number. And the last thing we have is, what is delta for that picture over there, delta T? Again, the 99% rule, go to the graph, see where the temperature approaches 99% of the free stream temperature, and that gives you delta T. So delta over delta T is about equal to Prandtl to the 1/3. So the first step is you find delta. Delta right there. Step 1. Let's go to step 1. Step 1 of these problems. Calculate the Reynolds number. Don't forget fluid mechanics. Step 1, always calculate the Reynolds number. Tremendously important. Okay, get the Reynolds number. We're going to find out, now don't forget, all these boxed equations over here, except the differential equations here, they're all, well, that's also true for laminar flow, but essentially laminar flow, laminar flow, laminar flow, laminar flow, okay. Turbulent flow is a week from Monday, so, okay, hang on that one. Get the Reynolds number, put it in here at a particular x, calculate delta, put that delta over here, put the Prandtl number in, Prandtl number. Prandtl number. And my Prandtl number, 2 ways to write it. We'll do it this way first. Our mu Cp over K, which is also equal to our nu over alpha. Nu over alpha. Isn't that interesting? The ratio of nu over alpha is defined as a Prandtl number, and it appears right here. And remember that I said there's alpha and there's nu. There must be something about that because both those equations are very similar, except one has a fluid property nu, the other one has a fluid property alpha. Yeah, it pops up here. We call it, we give it a special name, the Prandtl number, and it pops up in the equation here. Okay. All right, we got that. Let's take a look at what that means about the relative size of the boundary layers. I'll put that right here. Okay, let's take a couple fluids at normal conditions, ambient conditions, temperature. Okay, let's take air. Prandtl number is, at general conditions, about 0.70. So let's look at what the Prandtl to the 1/3 is. About 0.89. So that tells me that delta over delta T, 0.89. Delta T is bigger. Here's the velocity boundary layer, okay? And then our delta T is bigger. Let's take another popular fluid, water. Prandtl number at normal conditions, around 6.0. Prandtl to the 1/3, 1.8. That means delta over delta T is 1.8. So in that case, let's show delta. Delta is up here, and the temperature boundary layer then would be delta over 1.8. So there's the relative sizes of the two boundary layers. Notice delta is about double delta T. And now let's take another popular fluid, oil. For oil, the Prandtl number is very, very large, 6,400. 6,400. Prandtl to the 1/3, 18. Delta over delta T is 18. So here's the flat plate. Here's the velocity boundary layer, delta. Okay. Here's a temperature boundary layer down here. Boy, the velocity boundary layer is tremendously thicker than the temperature one. Of course, oil's very, very viscous. Air's not very viscous at all. No surprise. Oil, real viscous. Water, 2-to-1 ratio at normal conditions. Okay, so that shows how those thicknesses here vary, delta T and delta in the picture right there. Okay, now one last thing. This is all for laminar flow. So these equations over here, laminar flow, don't use them in turbulent flow. I'm going to add the other one. Laminar flow only. Everything on this panel of the board is for laminar flow only. Laminar flow, Reynolds number. Okay. The magic Reynolds number, if you had MA312, this is not a pipe. This is not 2,300. That's a pipe. This is a flat plate. Probably MA312, yeah. MA312, 5 times 10 to the 5th, magic number that we'll use. If Reynolds X less than 5 times 10 to the 5th, flow is laminar. If Reynolds number is greater than 5 times 10 to the 5th, flow is turbulent. So these equations only hold for a flat plate. And what does the Reynolds number depend on? It depends on x. So at a certain value of x, if the plate's that long, the flow is going to transist from laminar to turbulent. It will start out laminar. And at a certain Reynolds number, down here somewhere, it might transist to turbulent at that particular Reynolds number. So you have to choose the right equations for each particular area. These equations are the ones for laminar flow. All right, we're going to do turbulent flow then week from Monday. So that's a good stopping point here, good break point.